Well, welcome to this, our last of the SciEM Financial Maths and Engineering online seminars for 2024. We're very happy today to have Jose Blanchet from Stanford, who will be speaking to us about how to infer the quality of online stochastic optimization with infinite variance and why we should care about this. Jose is a very well-known person in operations research and related areas, so it's a great pleasure to have him here. Questions? Jose, do you want questions during the talk or keep everything to the end?
Questions during the talk is fine.
Okay, so if you have questions, please put in the Q&A or the chat and we'll raise them with Jose.
Great. Okay, well.
So whenever you're ready, Jose, take it away.
Thanks, Sam. Sorry, I had to turn off the stove. I just realized that I left something burning. Okay, so thanks very much, Sam, for the invitation. It's a pleasure to be here. It was difficult to select the topic, but I thought this could be interesting, hopefully a little thought-provoking. I think one of the surprising things in the talk is that some of the results were are new, even though you would imagine they are easy to guess for people who have experience or for on Levy processes and stable distributions and so on. And I think maybe one of the also takeaways of the talk is that these types of models might be more common, or maybe the environment in which they are appropriate might be more common than what one might think, when you first are presented with them at first sight. And so that's the second part of the title, why do we care about this? So this is a recent paper we posted. There is another one in the works that I'm going to discuss as well, that will hopefully be posted after the winter break. This is joint work with Aleks Mijatovic, and a postdoc, Wenhao, who is on the job market. His first year as a postdoc, he's quite remarkable. He didn't really know about this area on heavy-tailed distributions and Levy processes when he joined the group in last October. He had been working on different topics on distributionally robust learning and optimization. He really has led a lot of the research that I'm going to present here. So, okay, so here's the setup, right? So you are doing online optimization, or you are doing a stochastic optimization with some sort of budget constraint that, leads you to a situation where, okay, you are done using your budget, you have to make a decision, you have to kind of output, and now you want to make an inference about, okay, this is what I could do. This is what the data, given the data I have collected, how good is my decision, right, at the current step. And well, that forces you to, of course, create a model for the error. And a very natural one to use, of course, is normal distribution. You approximate means and variances based on the data that you have seen. It would take you like half an hour to figure out what the right variance is based on the data, right? To make inference on the decision could be a vector. So in the context of portfolio optimization, a vector of weights. It could be the error of some sort of utility. You maybe use a loss to train your portfolio, but you want to also make inference about what would happen with other different criteria, other losses, other utilities, and so on. So you need an error of kind of like, okay, what's the optimal portfolio roughly, or how far am I from the optimal portfolio? And you can use that to make inference, right? And so this makes a lot of sense, right? But what happens if you have infinite variance? And of course, the first thing that comes to mind is, well, that's an interesting academic question, right? I mean, but maybe this shouldn't happen that often, right? It should be rare that you have this situation. For example, you might think, in fact, philosophically, maybe it doesn't even make a lot of sense in some settings. I mean, if there is finite amount of money, surely the returns have to be in principle even bounded. So the correct model is the finite variance model. So this, although maybe an interesting question, maybe doesn't have that much of a practical relevance. And what I'm going to argue in the next slides is that really this issue of infinite variance is just an approximation to say that what happens is that you observe uh, the dynamics of the process behaving over certain time scales more closely to a process that has infinite variance than a process that has finite variance. And therefore, if you are going to make decisions in the time scale of the order of the data that you have collected and the characteristics of the variance that you observe in the data that are consistent with infinite variance, you should be using a model that is more, that extrapolates in that regime. And the thing is that apparently this sort of situation happens more often than you might imagine. So in the next slides, I'm going to describe examples where you can actually see this, and some of them might be known to you, some of them might be unknown, and then we'll go from there. And that's why I think this question is interesting. So we're going to talk about why do we care about this question and these examples. What's the philosophy basically that motivates this study? And then I'm going to tell you the results, and then I'm going to come back to examples where we are going to see different phenomena that happens when studying stochastic gradient descent in this setting compared to the standard sort of like Gaussian type error noise, and then I'm going to conclude. So, just to set the stage, what is how like the canonical distribution I'm going to be interested in using to build these models looks like, at least in one dimension, is is the Pareto distribution. Something like a Pareto distribution is an alpha stable distribution. I'm going to give the definition later in the talk. But basically, the idea is that you have these distributions that in the belly sort of have more are more peaked than Gaussian, and then that in the tails they are fatter, right? So this is the sort of picture. This allows me to also introduce the notation. Alpha in the talk is going to be a key sort of parameter that will dictate the way in which the tails behave. The case where alpha is larger than 2 is the case where you have finite variance, of course. And we are going to be interested in the cases where alpha is between 1 and 2. So X's are going to have finite mean, but infinite variance. Yeah. So examples of situations where you see, heavy-tailed data. If you look at the losses of hurricanes in the order of, in the time scales on the order of hundreds of years, you collect data in the time scales of order decades, right? So that data is consistent with a fit of alpha that is between 1 and 2 indeed. So in other words, like if you collect data and you make policy decisions about how to allocate federal emergency management agency allocations that are on the order of decades, for example, or tens of years, the inference that you should be using, perhaps in terms of whether that money is enough, should be one in which that is consistent with a model that has infinite variance. Of course, we have finite amount of money, but over those time scales, errors are going to be better predicted with that model of variability. That's the bottom line. Stocks. So this is a phenomenon that is also reported. This is we took it from a paper of 1992. This actually, you see this phenomena happen more often in, for example, blockchain, sort of Bitcoin and other types of assets and during periods of time of very, very high volatility, if you look at returns that have relatively high frequency, at those frequencies, it doesn't have to be super high frequency, just daily returns, you are going to see that dispersion and inference perhaps is better approximated with a model that has infinite variance. The key parameter here is 1.6. The other ones you can ignore. And so once again, so you're gonna do portfolio optimization on the order, collect data on the order of days or faster hours, and you're gonna make an inference on the order of like, a month, or your strategy you're gonna hold at that time scale. The idea is that fluctuations and inference are better predicted with a model that has infinite variance. Another type environment is in during the pandemic, there was some studies that were counting the number of deaths in counties and across time. I think this is LA County, if I remember correctly. No, this is all the counties, and then I think the next one is the LA County. Yes, so you look at all the counties during one day in that at that period of time, April 2021, and then the fluctuation of the number of deaths, right, over counties. A spatial fluctuation was better approximated by an infinite variance curve. So of course, once again, we have finitely many people, right? But decisions that affected policy over those spatial scales during that week in April, inference based on statistics of counties, uh, could be better approximated by a model that has infinite variance. That's basically the story, right? If you look at over time from 20 to 22 in LA County, once again during that time, COVID deaths better fitted distribute the behavior of a distribution that has infinite variance. What I'm plotting here is the maximum, is the running maximum of the deaths, and one characteristic of finite variance models is that during that statistic in particular, as you sort of track it, it should grow in a way that is little lower than a square root of n. So what this plot shows is a log-log plot. This slope, the orange slope, is 1.9. The slope that basically dictates finite variance models is the green slope, is 1/2. And so a finite variance model we should have some jittering at the beginning, but then it should be consistently underneath the green line. So one quick way to kind of see whether you are in a situation like your timescales and the fluctuations in a space and timescales are consistent with a model that has infinite variance is to just run these tests. And if you look at the data that you are collecting that is relevant for your inference over those timescales, and you're going to make decision also over those timescales or comparable timescales, then you're in this situation in which a better model of inference is an infinite variance model. So this is what the plot is sort of like indicating. Something that I think is quite interesting in machine learning. So this is an experiment from a paper of Mert and co-authors. So what they did is they look at deep neural network in data that is very popular. So this is CIFAR10. So AlexNet is a popular network. It's now is dated, but it gives you a sense of what I'm going to describe. So what they did is they computed the gradient of noises using that architecture. So for loss classification laws, you look at that type of architecture, AlexNet. You take the gradient, you take a sample from the data, CFAR10, and then you look at the histogram of the norms of the gradients. That histogram looks like the one in the blue. Now, if you were to just take a Gaussian vectors, right, and you take the norm of the gradient of those Gaussian vectors, right, and you try to kind of calibrate the mean and the variance, um, you would get something that looks like this orange one. So you calibrate this model relative to the data in the left-hand side, and you get this plot. That's what they did, the orange plot. You now simulate different Gaussians that have been calibrated, and you obtain this one that doesn't really resemble the model of how dispersion in the norm of the gradients look like. But if you fit a stable distribution, then you kind of see things that are more similar. So you fit that, and now you generate random noises with that stable model. You kind of replicate how those look in the data set. And so this turns out to be even more prevalent in more complicated architecture. So this is, as I say, it's kind of a little dated architecture, but in the context of transformers or the context of more complicated networks, you have that phenomenon happening. So that's also reported, right? You have these heavy tails, and that are often consistent with infinite variance. And in this situation, even though you have a lot of data, you have it's very, very expensive to train them. So the context is that over the scales of data that you can sort of parse and sort of explore, given your computational budget, again, you are going to be done with the computation. You want to make inference, then an infinite variance model could be a better choice because of the behavior that we have been discussing. So the bottom line is that one sort of like a quick and dirty way of monitoring whether your inference model is an infinite variance model might be a better inference model is just keep track of the running maximum of the gradient of the norm of the gradient. The running maximum has to be growing smaller than 1/2. So if you run a log plot, the straight line with a slope 1/2 should dictate. If you are below, then you are in an environment in which indeed the Gaussian model is the right model. If you are above that environment, above that green line, then maybe the infinite variance model is the right model. And so that's a situation in which the infinite variance model is the correct model. Here I'm showing a situation where, they kind of roughly are the same. That's, the alpha equal to 2 turns out to be maybe just an edge case. And so alpha equal to 3, then the slope is like about 1/3, and then it's slower than the green model. Now, why does this happen, even if the noise could be, have light tails? Well, this is a topic that is of very classical in probability. So I'm showing a version of a very classical result of Harry Kesten that explains why that happens. And this happens, for example, in recursions that are roughly like, kind of linear recursions than the one that I'm showing here. So if you look at this, model like this, the mean of the ANs, these are stochastic, IN and BN. You iterate the recursion. If on average the mean is of AN is less than 1, then this is going to be a contraction. It converges to its stationary distribution very, very fast. But if the probability that this AN is larger than 1 is positive, so occasionally you have inflation instead of contraction, then you are going to obtain heavy tails. And that has been, used to explain why in some canonical models in machine learning, you can see this behavior directly. So I have I have seen this. I have explained. I have written the case of linear regression in particular. So if you look at what the stochastic gradient descent iteration looks like, I just computed the iteration here, compute the gradient, and I run it, spelled out the details here, just to the point to show that just already in this linear regression case, you can see the iteration sort of very similar to that of Heston and the Heston result, and you can already apply the result almost directly here. This x squared sometimes is going to be very high, and this quantity is going to be less than larger than one in absolute value, and so you indeed have this situation where, on average, right, if eta is small enough, it contracts, but occasionally can expand, and so the stationary distribution in this constant step size stochastic approximation algorithm indeed is going to have heavy tails, yeah? And you can compute the exponent. And it could happen that the exponent will have infinite variance. That thing doesn't follow directly from this. So another way in which you can see infinite variance happens, well, sometimes you actually want the infinite variance. This is another reason why we are doing, we were interested in this project, is sometimes it is desirable to have them. There is a class of algorithms that are used, again, in machine learning. You inject the infinite variance because it allows you to escape local minima. So you run a stochastic gradient descent, and there are results that say that if you inject infinite variance and you clip, you can control the clip size in such a way that you can avoid sharp local minima. So you can basically, the occupation measure of the constant step size stochastic gradient descent is going to be concentrated on local minima, but this local minima will have, certain curvature that is more flat, basically. And by controlling the clipping, you can avoid some local minima that are not flat enough, basically, right? So that's, you inject the infinite variance basically on purpose. So it could come because of this multiplicative aspect, and if the neural network is deep, you're going to have lots of products when you apply the chain rule in computing the gradient. Or it could be something that you add. And, so it's something that you observe. And I told you how to monitor that. It's something that might arise. And the mechanism could be these gradients, these multiplications, or it might be something that you inject. And because of all of these motivations, we are interested in sort of finding what's the right way of doing inference for a stochastic gradient descent in these settings. So hopefully I have given enough motivation to explain why these models are interesting, are not just, not from an academic standpoint, but also from a practical standpoint. I explained how this can be detected easily, at least, and then how this phenomenon can happen. And now we're going to talk about distributional approximations in the output analysis of SGD. So this is the notation I'm going to be using. I'm going to be interested in minimizing expected loss and the iteration of a stochastic gradient descent I'm explaining right here. Through the rest of the talk, the parameter eta is going to be the learning rate, and now we're going to be talking about how to make inference about this. So one application could be when to decide to stop. If you have enough, if you have when to continue. Sometimes you don't even have that luxury. It's not that you want to stop. It's not up to you. It's just have finite amount of budget or finite amount of data. And there are many ways of doing, measuring the error. Some of them could be time consuming. Sometimes you can use some non-asymptotic bands, but they can be very, very conservative. They tend to be very, very, very conservative. And it's hard to get something, you typically assume, sub-Gaussian tails or truncated distributions, and is more difficult in the infinite variance setting. So what is it that we know, right, in the finite variance case? In the finite variance case, we know that the optimal rate is obtained by something that is linear, linear decay. But you need to choose this constant. In the multidimensional case, this C is a matrix, of course, and that matrix needs to be large enough in the sense of the cone of positive definite matrices. So you pick a positive definite matrix here that is very large enough. Could be just a diagonal matrix, but just the constant should be very large. If a function you want to optimize, in other words, this L function here, L bar, is lambda convex, strongly convex with curvature lambda, so the C has to be larger than this 1 over 2 divided by lambda, so large enough. So sometimes it's difficult to get that C well properly calibrated. So what you do, or you resort to a suboptimal rate, right? So this C, the learning rate now becomes n to the power minus gamma. Gamma is a number between 1/2 and 1, again in the context of infinite variance. Otherwise, it's going to be 1 divided by alpha. So the rate is suboptimal, and the distribution will depend on the C. The variance, is going to be a suboptimal variance. Now, what you do is you do this very cool thing, Paul-Jack-Rupert averaging. So you just average your iterates, and that's a really cool result that says that then by doing that, you recover the item number 1, so the optimal rate, and now it doesn't really matter. You don't really need to think about how to select the constant C. So that's really cool. So this talk is going to be concentrating on the case gamma less than 1, just because of expediency, and also because I'm going to talk a little bit about what's the analog of Paul-Dirac-Rupert averaging here. Turns out that there's still the same types of results holds. You can recover the optimal rate under some assumptions. And so that is also pretty cool. So I'm just going to concentrate on gamma less than 1 and C equal 1. So once again, like just summarizing what is known in the finite variance case, I'm going to assume here it says regularity conditions. So one of the surprising things, as you will see, is that even though this is like a very classical question, not that much actually is known about the infinite variance case. So I'm going to start with the easiest case. You have locally strongly convex function, so that's the regularity condition, and you have finite variance. And in that case, when the rate is n to the minus gamma, the error is normal, and you can describe the normal distribution as the stationary distribution of an Ornstein-Uhlenbeck process, as the one that I'm kind of explaining here. So this is the Hessian matrix, and then you have this the basically covariance of the gradients, right? So it's not quite, I mean, they have to be centered, but you can think of this as the covariance of the gradient, and then the Hessian is what drives this Ornstein-Uhlenbeck process. In the infinite variance case, okay, so this is one thing that when we started this project was a little surprising. I mean, what is known is well understood, the case of the one-dimensional case. So you need so you need regular variation, of course. So that's something like Pareto, but with you can have a slowly varying component like a log or the power of a log multiplying the tail. Um, the particular result of this 1969 paper, I think, involves what is called the normal domain of attraction. So, namely, situations where the limit is you don't have like a slowly varying piece. And then, if you with the scaling that I gave, 1/n, so scaling it 1/n to the power gamma. Um, you scale it like 1/alpha minus 1. So if alpha is equal to 2 and you basically have finite variance, then this is you recovered the n to the minus a half. Yeah. So we are in situations in which alpha is less than 2. So that's the right scaling, and you converge to something that is like an alpha stable distribution. So the multidimensional case has been studied recently. So this is a nice paper. Again, this team has, I alluded to some of the experiments in machine learning in coming from computer science, where they observe these finite variances, and this is that community. And they maybe they were motivated by a class of algorithms that are called perturbed gradient descent. So what they did is basically look at, you inject the noise, and the noise doesn't depend on the state. So at every point in time, you take the gradient and you add something that has infinite variance. And so that's your model basically, right? So it's not the type of result that you could use in sort of online optimization, in which the gradient itself and sort of the infinite variance part depends on the state. Yeah. So that's what we we call it additive noise. They also consider the normal domain of attraction, namely, is basically asymptotic Pareto. And the limiting distribution is not characterized. It's just simply, under this scaling and under this normal attraction domain, you obtain a distribution that is alpha stable in the dimensions, but they don't obtain what are the characteristics in terms of the process itself. And basically that's it. I mean, that is also one of the things that I think is interesting in this sort of like landscape of the literature. And so, are there questions so far, by the way?
None yet.
Great, thanks. So, comparisons, right? I mean, we are going to be, I'm going to compare what is the analog here. And so for those of you who are familiar with the theory of just simply a stable convergence of an empirical sum of ID random variables, um, it will be easy to see what is the key element to obtain these types of results. So what is that theory? How does that theory look like? It's very, very classical, right? So when you have finite variance and you normalize IID samples that are centered, that have finite mean, convergence of the sum is dictated by Donskir's theorem, and it goes to a Brownian motion in DC zero infinity topology. In the infinite variance case, something very similar happens. Again, I'm describing the normal domain of attraction. Namely, there is no logarithmic correction, but the paper deals with the general regularly varying case. So in that case, when the tails are almost like Pareto or asymptotically Pareto, the we tail t to the minus alpha, then the scaling looks like this. It converges to a Levy process, which is a stable process. So it has stationary independent increments, and you can describe it using the Fourier transform. So, just
Sorry, Jose, there's one
yes.
question that's come up from Kami Ayati. Why Pareto?
Ah, that's a great question. So let me just Pareto is you don't have to have Pareto, right? It just the description that I gave is you can replace this equality by an asymptotic approximation. You can stick also a logarithm or logarithm square. Then in that case, you will have to change the scaling at the log, right, as well. So that's what I mean by Pareto-like. And the reason and why Pareto-like, um, if you don't have that type of regularity in the tails, um, then you might not actually have a result. Like for example, if there are many ways to have infinite variance, and if your distribution, for example, it doesn't change regularly in the tails, then you might have fluctuations in the weak limit as well. So you do need when you go beyond the finite variance case, the turns out that this type of limit theorem is obtained by go back to this limit theorem. The way to prove this thing turns out is is driven by jumps, very large jumps, right? So what the whole thing here, you look at the jumps that happen that are order n to the minus n to the power 1 over alpha in n observations, and that turns out to be a Poisson process, Mark Poisson process. So it's everything about the tails, and if you don't have that regularity, then you might not get a limit. It's very easy to construct samples. So in the infinite variance case, it's a game of extrapolation, and to extrapolate, you need to have regularity, and basically that power tail. I don't know if that answered your question. I hope it did.
It did. So thanks in the chat.
Got it. Thank you. So okay, so this is a picture. So this is just a simulation of an alpha stable process that goes from infinite variance from alpha between 1 and 2. So the end of the simulation is barren motion, and everything in between is actually the same seed, the same process, just changing alpha. Okay. Okay. So the obvious conjecture, right, is that okay? So you in the finite variance case, I take this guy here and I compute the stationary distribution, and this is what I use as my model for inference, right, of the stochastic gradient descent algorithm. Well, obviously, the obvious thing to do is to just take the Brownian motion, replace it by something that is this stable thing, right? And yes, this is exactly what it does. It happens. So this is going to be the basis of the result. This is actually very, very direct. Is the hard part, if you will, in this result mathematically is just to get the right assumptions, to be honest. Once you find the right assumptions, then you just turn the crank and then it's very easy. The one that is more interesting, so this is for finite, this is constant step size stochastic approximation. The one that is a lot more interesting is the decreasing step size stochastic approximation. That one is more complicated to analyze. But you can sort of start warming up, and that was a great for Wenhao because he was able to kind of learn this and very quickly get something interesting. So the first, as I say, constant step size stochastic approximation. So you embed the algorithm on a constant rate in this recursion. So this is the same recursion. I just kind of labeled the recursion in the real time line in the last lattice of size eta, and then we look at time steps of order, like the whole in real time, wall clock time order one, but that corresponds in the description of this algorithm, time steps of order 1 over eta. So fluctuations of size eta, and then you have a law of large numbers here that again is quite standard and just requires finite means. And now we are interested in fluctuations around this gradient flow. Okay. And so the assumption that I was alluding to is, okay, so you want this vector to be regularly varying. And what do we mean by this? It's a vector field, right? It's not, now um, it's not a, it's not a fixed regularly varying distribution. It's a random field, right? That is indexed by this theta. And you want this to be regularly varying. So what does that mean? It means that, there would be a function here that depends on, so we're going to scale this by x to the power 1 over alpha. And there is this function that basically is here to accommodate things like logs and things like that. So it doesn't really matter that much, but it's to emphasize that it's not only Pareto, it's not just the normal domain of attraction. So you can do other things that are more interesting. And so the point is that this will converge to some measure or a set of measures vaguely that are indexed by theta, and they have to be, and these functions, so measure valued functions, right? So for every theta you have a measure, they have to be continuous in theta. And so another way of kind of saying this definition, if you will, is like this. So you have when you normalize this vector, so the gradient divided by its norm, this is a point in the surface of the sphere. You condition on the norm being larger than t, and the limiting distribution, which is on the surface of the sphere, um, depends continuously in this parameter theta and is asymptotically independent of the distribution of the size of the gradient, right? So um, that's what it means, right? So basically, in the end, the size of the increment and the angle, they are asymptotically independent, and the distributions depend continuously on the parameter theta. That's what the assumption means. So under this assumption, then you have convergence, weak convergence in DC zero infinity to the process that we conjecture. So that's, you basically you can recover exactly what the process is, and based on that assumption, and that's the difference. So there are two differences with the results of this 2021 paper in computer science that I mentioned. So there are three differences. One difference is that you can now use logarithms. So you have a more wider family of infinite variance distribution. So that's the role of this B. You can stick in like their log or something that is not just constant. The second difference is that you can have dependence of the parameter theta. So is the limiting sort of measure, or the noise is not independent of the position of the algorithm. And the third thing is that by doing this, you can recover exactly what are the characteristics of the L process, so you know exactly what the limiting law is. Now, again, this is the easy case. I'm going to talk about the other case in a second. So that's the case where you have constant step size and you track the algorithm in time steps of order 1 divided by the step size. Okay, so also quite interesting here is that this distribution doesn't have to be symmetric. So the stationary distribution of this process could be quite asymmetric. So the one in the Ornstein-Uhlenbeck is Gaussian, and sort of it's after an affine transformation, you can make it completely symmetric, just a ball, right? If you multiply by the square root of the covariance. This is something you cannot do with these types of processes. And even if everything was symmetric, like that is the noises were symmetric, right? The evolution of the gradient could make the distribution non-symmetric. So in the context of this, the way people use this in computer science, if you add noises, perturbed gradient descent that are just symmetric, alpha stable distributions, like or symmetric infinite variance, right? The T distribution. After you pass it through the gradient, then you can create all sorts of non-asymmetries that do something to the limiting process in a quite interesting way, as I'll explain. So the distribution of this one, by the way, is a time inhomogeneous Levy process, and so it can be described very precisely in terms of the assumptions that I gave earlier. Right, so you can describe what are the characteristics of the process, and you have the center of the process is this function that depends on the limiting measure and depends and tracks the evolution of the gradient flow, and so everything is quite explicit. Now the other result that is more interesting is, okay, so now you want to send the rate to 0. You look at the stochastic gradient descent once again, and now you have the same type of result that you can conjecture. So the conjecture would be you look at this process, right? You take kind of like a double limit. You take this process t, you send t to infinity. That now you get a process that is so you would look at the characteristics and you replace this by the limiting point. So theta bar just becomes theta star. Now that becomes a time homogeneous process, right? That will be this t equal to infinity. So that will be like as if eta is equal to infinity in the first limit, right, for the gradient flow, and then t to infinity in the gradient flow. So this theta bar becomes theta star. That's what you would look at exactly the same process, just replacing theta bar by theta star. That's a stationary process. And then you look at the stationary distribution, and that is the one that is your conjecture of what would be the stationary distribution, the distribution for the fluctuations, right? So that's exactly what this thing is. So everything is exactly the same, the previous SDE, just replacing the gradient flow by the limiting point. Then this L becomes a homogeneous Levy process with the characteristics I described. And then your result will be that's the limiting distribution. Now, the difficult part here is precisely what I alluded to. So if you think about how to prove the results conceptually, you basically are looking at the constant step size over time horizons that are 1 over eta, but the time horizons become eta decreases, so the time horizons become larger and larger and larger. And the input of the next iteration of this process is the output of the previous one. So it's a random point. And so the hard part is to make sure that along this sequence, the input is tight. Yeah. So that's the thing that was not so easy. And at the beginning, we have a proof that was very long and needed to extend some results on large deviations for heavy tail random variables. In the end, the one that appears in the paper is a much simpler version that uses some symmetry argument and a way to couple with just Levy alpha stable Levy processes. So that was the hard technical part for this. Okay, so I want to show you one example that I think is quite interesting. So, you can now apply to linear regression In the linear regression case, we computed what this limit is, and this limit is in fact really not that interesting because it doesn't depend on theta. So the linear regression case actually doesn't, this v function is independent of theta. So it's not it's easier in a way. So it's in that way, in that sense, is kind of similar to kind of optimizing something that is like quadratic and adding yourself. You add the gradient noise yourself, right? Independently of where the position of the random of the algorithm is. So that's kind of similar to this. So it's similar to something like this where you add the noise. So that's what I'm describing here are the trajectories of the limiting SD. So that's not that interesting. Let me jump to the other one because I'm running out of time. The other one is a lot more interesting. So this one is logistic regression. Here, what you're gonna do is you would, you can compute. It's a much more complicated, but the point is that now this this the v function or this key object, which is the gradient, normalized gradient, now converges to something that depends on the sign of this is your predicted y, sorry, y of theta. So that would be this y really means is like your prediction that the probability that y is equal to 1 as a function of theta. That could be 1 or -1. So how do you assign the value of y given the current position of the algorithm? So it could be negative or could be positive. And so now this means what this means is that this object here is going to be concentrated on rays in the surface of the sphere. So if just in one dimension, what it means is that if theta is positive, then you are going to be trying to go up. The error has a tendency to go up. And if the theta is negative, the error has a tendency to go down. And I'm not so even if the algorithm the gradient flow tries to push you up because the correct parameter is up and you started down at the beginning the error is going to have a bias towards going down. So that's the interesting thing. So let me be more precise. So suppose that in this logistic regression model, the true parameter was 1. Okay. So the noise has infinite variance. Um, the distribution will be asymmetric. And we have two initial conditions. One could be -1, the other one is positive, right? So what I'm saying is that as long as the algorithm at the beginnings, right, if you're going to be exploring negative values of theta, if you start with -1, as long as you are over the course of the algorithm on the negative region, the jumps in the positive region of the error actually are going to be they will have very low probability in the prelimit. So in the limit, the jumps have positive jumps do not happen. Even though what is going to happen is that the process is taking you up, and so the mean is the one that is moving, but the fluctuation is going to actually take you down, and that has implications in terms of your inference. If you start from the wrong side, right, your error is going to actually is going to have a tendency to be more wrong. That's the point, right? So, so let me show you an example here. So this is the case where this is the error. So the error is is the difference between the value of the algorithm and the true value scaled. So this is it, value of the algorithm minus what you're tracking, right? Scale. So something gets stuck here. Sorry. So yeah, here. So let's look at this plot first on the top left corner. So this one starts from -1. The error, what is this? Yeah, the beginning, both the process and the gradient flow, they start from the same value, -1. So the difference is 0. And then it tends to go, it tends to increase, right, on the negative side. So and then it just flips and goes up, right? So this kind of like a change point here happens because around this time between 0 and 1, the gradient flow actually touches 0. So if you look at here, you somewhere here in between, it touches this 0 here, and then it just goes positive, the values of theta. And so now you flip and then you try to go up. You have that the bias in the error as it described goes up. If you start from something that is on the correct side of the decision, theta star, then you don't see that, and the error goes up and down all the time. So that I think is also an insight out of the analysis here. So the conclusions, I think I have convinced you that heavy tails provide a modeling formalism for wide fluctuations. They happen more often than one might think. You can use the theory of Levy processes and you know to do inference with this stochastic gradient descent with this type of models. There is new phenomena that happens with, compared with the standard finite variance case, as I showed in the last examples. Was quick, but I am happy to answer questions. And I think these results can be helpful, hopefully, in this multidimensional setting. Surprisingly, for the first time, given that this is the math is frankly more or less classical and not entirely trivial for these results that I mentioned, but is well known in the probability community, but is the first type of results of this kind anyway. And I think that's it. I think my time is up, right?
Thank you, Jose. So, as Jose says, our time is up, but we can hang around for a little bit for some questions. I suppose I was wondering, this initial fluctuation that you see in your limiting behavior, does that change? Does that give me insight into when I should be including more heavy-tailed behavior in my gradient descent, if I have any choice? So is there an argument to not use heavy tails early, run it for a little while, and then hit heavy tails to try and get the advantages later on without this initial fluctuation?
Right. I mean that's a great question. Like, to be honest, yeah, you could use that insight in the way you describe. Maybe not quite like early, because very very early doesn't really matter, and maybe you want to explore fast. But maybe indeed what you, as you suggest, like maybe you kind of like if you realize that you have over the course of the algorithm you have a way to do batching, right? And based on that batching, you can sort of see that you confidently are not in kind of an exploration mode, but you know that you are on the wrong side, right? I mean, this example, and you say, well, actually is not helping today's infinite variance if you are on the wrong side. Yeah, I think understanding what's the nature of this fluctuation. There are multiple ways in which you can do it, but that definitely is one potential use of this insight. Yeah. Thank you, Sam. Yeah.
If there are any other questions, please either raise your hand or post in the Q&A or the chat. I suppose one other thing I was thinking about, one of the classical problems, say, with your very early examples of insurance payoffs, etc., these real world heavy-tailed systems, is that you generally get very little data in the tail. So you might get the heaviness of the tail, but there's not a lot of data out there. There's only been one Hurricane Katrina, one of these extreme events, or relatively few that have gone as far out in the tail.
Correct.
And this means that I'm sort of a little bit worried about doing anything that really relies on the heavy tails, just because it depends so much on individual moments.
Yeah. That's a very fair point. Like, so this got stuck, but so there is the thing with this regular variation is that it is that, right, regular. So to what you do that to mitigate that is you kind of look at um, the tendency over which you are actually seeing these extreme things, because you have things that are not so extreme. So it's about is the shape. So if you remember, this got stuck. I don't know why, but in the histograms of this Alex net, right? I mean, there was something about the way in which in which in which the you see here other things that are not that extreme, sort of here.
Mm-hmm.
And if you were to kind of like, you see, it's something about the way this changes, right? So at the beginning, I think I would just throw away this stuff. But there is like an intermediate scale where you actually have data and you can look at how this varies. And I agree, like if it's just about these 3 points, right? Then maybe you are giving these 3 points a lot of importance. But then,
Mm-hmm.
if you look at kind of like this here, there are like 20 points here and somewhere here, then you say, well, yeah, maybe over these timescales, indeed, there are more um, jumps in the returns that I should have expected otherwise. So I'll tell you what the best result for me would be, and this is what we're trying to do, is something that is just data driven, right? Something that actually kind of just don't worry about it. You calibrate that. And something that is in between these two things. Like now the distributions that are right there are called tempered stable distribution. So there is, and that's what we are doing right now, right? So something that is just don't worry about it is going to pick it up. Do you know what I mean? So
Yeah.
a tempered distribution is one where you start from something that is heavy tailed, but you introduce a truncation, and then you can do this double limit in which you send the number of sample points to infinity, but also that could depend, the truncation depends on that. And so over the correct sort of speeds, there is something that is right in between, there is something that is Gaussian, there is something that is stable. And that extra parameter sort of like allows you to interpolate right there in the sweet spot where you might have a little bit more data to kind of learn the shape.
So there's a couple more questions that have just come up in the Q&A. Um, I seem to be having trouble with Zoom changing the rules, so I can't enable people to talk. But Yifan Li says, thanks for your informative talk. A quick question for the last two examples. I noticed that there are some jumps in the error plot of the regression, but they do not appear in the logistic regression. Are there any reasons or intuitions behind it?
Oh, that's um yeah, so these things, right? These jumps um these jumps actually come from, you see alpha equal to 1.2. So the linear regression example has the property that it really doesn't depend on where the algorithm is. The logistic, this one, there are jumps. I mean, it's just Levy processes are a funny thing. So even though this appears as if this is continuous, the jumps are extremely tiny. And yes, it totally depends um, on the fact that this depends on the gradient and depends on theta. So you don't see the jump, but this is not a Brownian thing, right? This might look like a diffusion, but is not so. So there are little jumps here, but yeah, that is also a very interesting um, thing that happens with this model. The jumps are even alpha equal to 0.2. This appears continuous, but this really should be like a jump here from here to here.
And another question from Jose Henry Leon. In your early plots, are you fitting only the tails, or are you also including fitting of the full distributions?
In the early plots, so some of the plots, so for example, let me show you, they implicitly are censored. For example, this one, right? I mean, it contains everything that is characterized as a hurricane. Then there is, this one, I believe in this paper, it includes all returns. This one, it includes everything, right? I mean, it's this author. Well, this is Richard Davis, and so he knows how to do this. So he might have thought he might have dropped, some of the smaller ones. But this is done by people who actually know how to do this very well. So yes, they probably remove it and use some estimator that we know that these things need to be removed. And these other plots, basically, they are more in the spirit of extreme value theory because I just track the running maximum. So the running maximum just will censor those observations that are not very big. So this is, yeah. So, yeah.
Okay. Well, I think we should finish there just for the sake of time. So we'll stop the recording. Thank you again, Jose, for giving us a lovely talk. And a happy new year to everyone. We will be continuing our online seminar series in the new year. We'll be posting all the details on SIAM Engage as they're available. So thanks again and happy new year, everyone.
Thank you. Thank you once again, Sam. Thank you. Nice seeing you.